science? It starts with a D. Deep learning, right? So if I gave this talk 2 years ago, right, this would be all about deep learning. But what's the hot topic this year? What is everybody talking about? Interpretability, fairness, lots of that stuff. So we want to bring that in today. Now, once we start talking about things like fairness, trust, there's a lot of issues that come into play. And I only have an hour here. We're not going to be able to hit them all. So I just want to highlight that although we're going to focus on the tools that explain the model, when we start talking about being able to trust the model, it's much more than that. It's being able to, for example, make sure that the data we have that's underlying the model is not unfairly biased. This is often a common issue, right? That your model has an ethical person, that it remains healthy over time, the model stability, model monitoring, all those things come into play. But just want to highlight those issues, right? Lots of room for future talks, but for today, we're not going to hit those. But what I want to do is when we build this model to figure out if this dragon's going to eat us, what I want to do today is build an interpretable model, right? So we want to be able to understand this model, okay? All right. So why do we care about interpretability? Right? It's big in like the data science blogs, right? All that stuff, right? Big conferences. But what does it mean to you? What does it mean to us? Why should we care about interpretability? There's kind of 3 reasons I have. The first is, if you're the person that's building the model, you want to build the best possible model. You need to be able to understand what's going on in your model to be able to improve it, to correct any defects that come out of it. The second piece is, well, okay, you've built the model, but then you've got to go to your boss, maybe a customer, and they're going to be like, well, what's going on here? Can you explain what's going on? So there's another level of why we might want interpretability. And then finally, there's an outer level, and you can think of this as society as a whole. It could be because you care about all of society, or it could be that you're one of those poor people inside an insurance company or a bank that has all this model validation to go through. Right? When I worked at State Farm, any model that we wanted to deploy out, we had to first write a 100-page report on it explaining how that model works. So this is another area, is where you have, whether it's regulators, model validation, you need to be able to explain that model to them. All right. So let's start with the simplest, easiest models that we can probably all agree to explain. So this is a simple model to figure out, hey, can we figure out what the price of a house is going to be? We're going to use 2 features, bathrooms, square footage. We show you exactly there. We got the coefficients here, so it's very clear, very transparent. Is everybody good with that? Is this model confusing to anybody? Is this what we would consider an interpretable model? Okay. All right. Let me mix it up. So let's go to a little bit more. How about this model? So instead of just 2, and I'll use the term variables, I'll use the term features interchangeably. Instead of just 2 features, now we've moved up to 8 features. But I've still given you all the coefficients. Is this easily understandable? Yeah. In a room full of data scientists, it is understandable. But that's because you're calculators, okay? If you step back and look at this model, can you explain to me why the coefficient for total rooms is negative? So as I get more rooms in my house, the value is going to go down?
You've already interpreted, you've already built it into the model enablement to some extent.
I've already what?
You've already accounted for it with bathrooms and bedrooms for 2/3 of it.
But I mean, is that easily obvious to people?
No.
I mean, you're right, from a calculation point of view, we can kind of figure it out, but it's not easy to explain to anybody. And anybody who's ever built like a marketing model where you hand out coefficients to marketing folks where everything is collinear, right? It's not easy to be able to say it's because of this effect. The correlated features make it very difficult to be able to explain to anybody. So that's why even though we have kind of a linear model, it's not easy to explain. Okay, so this is where some data scientists might be like, yeah, linear model, who needs linear models, right? We've got much better tools than this, right? Let's go to decision trees. A very classic cart decision tree. So I had to switch it up here. This is Titanic. It's still about things dying, though. So here, is this an easily explainable, understandable, and kind of interpretable model? I mean, it's not too bad, right? If the person is male and the age is, greater than 10 years old, right? Most of those kind of die off, right? We've seen the movie. We know what's going to happen here. And so it's not that bad of a model. Now, how many features do I have in this model? 2 features. Is that enough to explain what's going on the Titanic? No, not really, right? The performance of this model is not that great. So we might say, you know what, well, let's try to improve the performance a little bit. So we might say, let's add in a few more features, right? Make it a little bit more complex, right? You can see on the left, bottom left there, the performance of this model gets better. It's more accurate, right? And remember, at the end of the day, this dragon's going to eat us, so we want a model that's good, right? We need to be able to understand this. But now we've got a few more features in this. Is it still pretty easy to understand? Yeah, pretty easy? Okay. How about if we add a few more features? Well, okay. Now again, the data scientists will come out here and say, well, I've got a better idea. When I want to improve accuracy, I'm not just going to use one tree, I'm going to use a lot of trees. Now, what do we call this in data science? A lot of trees? Forest, right? Kind of good old random forest. And the nice thing about this approach is we keep adding these trees, more trees, and we get a boost in improvement. Right? We're very happy with this model. What's the most important feature in this model? Right? Right? Good luck having to explain something like this to somebody. And I've only started covering the things, right? We talked about GLM, we talked about a random forest, but here's the thing is, in data science, there's a ton more different algorithms that are out there. So this is Randy Olson. He ran some benchmarks just using all the straight classifiers that are in scikit against lots of open source data sets. And this is kind of that no free lunch theorem, right? Depends on your data set for what algorithm's going to work best. There's some algorithm, some data set out there where multinomial Bayes, which normally isn't that great, works the best. But you never know this stuff until you run it. So this is the problem when we get back to explainability now is, now we have lots of different algorithms we have to consider to be able to explain. And the point is, right, the algorithms matter because you want to get that best possible accuracy out of the model. Okay. So let me kind of summarize where we're at here right now. We know these simple models, they're just not going to work, as well as if we want models that people can kind of understand what's going on in them, it's got to be really simple models, right? Anything quickly complex, it's just too overwhelming. If you're interested in more of this stuff, Briegman, classic paper back in like 2001, talks about the issues of multicollinearity, how that affects interpretability. The examples with the linear models I used came out of work by Porsabi. She talks about that and actually empirically studied that and not just kind of textbook ivory tower stuff, but actually asked people. There's another line of research around Kleinberg who talks about, when we talk about fairness, that maybe using a very simple model can actually be unfair, that maybe that complex model is capturing more nuance in society, and that's what's going on. And then Holm recently wrote a piece in Nature on the defense of the black box. So this is the idea that for some cases, it doesn't matter what the model's going on. A black box model is just fine. So just some ideas for future thought around this. Okay. But I promised you tools, so what I want to talk about today and spend most of the time talking about is that we have tools that for any of the models that are out there, that we can explain any block box model. Now, we only have an hour here, so I'm not going to be able to hit everything, but what I want to point out is there's 3 different things that we should we should think about when we have interpretable tools for models. One is understanding what are the most important features or variables in a model. We'll talk about that. Understanding their directionality. We'll talk about how you can use tools like partial dependence for that. And then the last one is explaining a prediction. Being able to take a row of data and understand what are the variables that are driving that row. So those are the 3 big tools we're going to talk about. I'll take a pause here. Any questions, any issues so far? Okay. All right, so let's jump into this. Let's start off with feature importance. Right, so think about our model for dragons. Before we build our first model for dragons, right, what do data scientists want to do? Is you want to understand the subject, right? Maybe go, I don't know, watch a few Game of Thrones, talk to some dragon experts, figure out what are the most important features when you're going to build out your model, right? And you might say, right, age, weight, gender, right? If they've killed before, seems to be relevant if you're trying to predict if they're going to kill you. Whether or not they have a spiked tail, right? Sometimes you just throw theories out there. You don't know for sure or not. You'll see which variable adds some signal in there. Whether they've had children, their demeanor, that sounds obvious, right? So probably kind of sensible things, right, if you're going to build a dragon model to do that. So one of the things we'll want to know in these models is which of these things are important in our final model once we start with. So I want to talk about this, but I want to first shift to a little bit of an example that we all understand a bit more, is understanding how dragons read. It's not actually dragons, but we have other people in our lives that learn to read. Think about how children learn to read. And I use this because we can understand this before we actually look at the data. How old a child is? Does that have an effect on how much on their reading ability? Probably, right? My 4-year-old can't read, right? 12-year-old can. How about milk consumption? How does milk consumption affect our ability, a child's ability to read? What's the directionality there? I mean, as you drink more milk, reading improves.
Are we talking human milk, cow's milk? Would be opposite.
Cow's milk. This is like stuff you buy, yeah. Because most people don't drink, I don't want to go into narrow things, but most people don't drink human milk after a couple years. We're doing the overlap of reading and milk consumption, so let's, keep the breast milk out of this for now. We get some bad areas here. Let's leave it at okay, and actually I had to research this myself because I had initially assumed that milk consumption, as your milk consumption goes up, your reading scores would go up. And for me, that seemed intuitive, but actually it's the reverse. Because what happens, right, is my high schooler doesn't drink any milk while my 4-year-old does drink milk. And so that's kind of the relationship there. Okay, but let's say we have this model here for kind of looking at milk consumption. Now we want to know which of those factors is most important. If we put this into a model, and this comes from Strobel and one of her papers where she kind of actually used this example, and we used kind of a default value, for example, in light GBM, which is a split-based variable importance, just counting up the splits in your trees, you'll see that milk consumption actually comes to the top in this example. And that's a little scary here because we know milk consumption has nothing at all to do with it, right? But it's just a little bit of the nuance of how trees work. That split-based variable importance can be biased to variables that are continuous that have lots of splits. But if we use a permutation-based method, it gets it right. It realizes that milk consumption really doesn't have anything to do with reading ability. So those are some of the example data sets I have that you can run. But this is when I want to focus a little bit on what this permutation-based variable importance is. Okay. And the idea here is we need to get this right because just like in that example before, if you didn't get it right and you thought it was actually milk consumption, well, you might set up your school to improve reading scores by getting rid of milk, right? And that kind of thinking happens all the time in enterprises with data scientists that run and build these models. As you look at the top 3 things on the feature impact and say, I want to create a policy to minimize or maximize these things. So getting that order really matters. Okay, so let's just jump into, let's talk what I mean by this permutation-based feature importance. So here's a very simple example of feature importance. Now what we're going to do is I have 2 variables, A and B. I'm going to build one model with both of those in there. I'm going to build another model with just feature A, another one with just feature B. It's a very simple example. To evaluate the performance of the models, I'm going to use R squared. For those unfamiliar with R squared, the higher the better. Just leave it at that. So in this case, when I combine both, I get the highest performance. But then when I have model A, I only get an R squared of 0.7. When I have model B, I get an R squared of 0.8. Which feature variable is most important in this model? B, right? Why? It's higher score. Yeah, this isn't too complicated. I told you that it was a higher score. Of course it's a better feature, right, than that. And that's one way of thinking about it, but I want to show you another way we can get to that same place. If we start with adding with variables A and B, and if we just remove variable B, how much does our model drop in performance? It drops by 0.2 from going from AB to A. On the other hand, if I just remove variable A, how much does my model drop in performance? 0.1. So that's another way of getting us to that same answer, that B is the most important. All right. So this technique of what I'm talking about is often called an ablation methodology. This is used all the time in empirical studies. How do you measure the effectiveness of something? You try it with it, you try it without it. Now, earlier we talked about deep learning. I used to do a talk on image classification, and I would talk about how I had my son, my 2-year-old, I would take him to the zoo and make him look at other animals and see which one is most dog-like, which one's more cat-like, to kind of see, could he classify those correctly. Same kind of thing here. Ablation methodology. We want to see what the impact of something is. So this is one where I experimented with my wife. So what I did was, on one day, I gave her coffee, and on another day, I didn't give her coffee. And by comparing those 2 days, I was able to see what is the effect of giving my wife coffee. It's an easy type of method to be able to see. Of course, she likes coffee, and I run away if she doesn't. What? Exactly. So, but you get the idea of the technique, right? We just try something with and without it. It's an easy way to evaluate the performance. So let's go back here. So I'm going to make it a little more complex. We've got 3 features here in this. So now take a look at this. Which feature here is the most important? A, B, or C? Somebody yell something out. C. So, because if we remove model C, if we remove feature C from the model, it drops the most in performance. Okay? Now to do this, we had to build 4 different models. As you can see, if you had, let's say, 50 features, 100 features, this is a lot of models you got to build out to try all these different variations. But this is where we can get a little bit smarter. What we can do is actually, instead of actually removing the feature from the model, we can use a technique called permutation or shuffling. What we do is we just take the feature and we just change all the values in a column. And by changing all the values, it's comparable to removing the information. It's comparable to actually just taking that column out. And so what this allows us to do is we don't have to have separate models for each different example. And we can use this as a quick way to understand what the impact of a feature is in or out of a model. So this is kind of goes back to kind of Bremen in 2001 paper that talks about kind of permutation-based importance. It was with random forest, but this is a technique that you can actually, is very model agnostic. You can use it with anything. It's also widely available. There's lots of implementations out there. So if you use R, for example, it shows you a permutation-based importance by default. For the Python fans, hold on. Unfortunately, sklearn only uses a Gini-based importance, but there's a ton of other packages out there that you can get a permutation-based importance. And this is kind of considered best practice when you're looking at that feature importance. Okay. Any questions so far? If you want to know more about permutation importance, Strobel's kind of classic 2008 paper talks about it. Scott Lundberg in his Shapley work has talked about it. There's some great blog posts if you just Google at Explained AI and Data Dive that talk about it. Whenever you're doing any of these methods in data science, there's often a trade-off between how long you want to sit and wait to run every possible combination, how long you want to wait, the computation versus time. There are more advanced approaches, like Baruda, for example, is great, but it just takes forever to run. There's the party package, and R is another one if you want more advanced ways to kind of do the feature impact. All right. So for how many people here this hadn't heard of permutation-based importance? Okay. And how many people have used permutation-based importance? There's a couple hands. Okay. All right. Okay. All right. So this, at this point, should give us the tools to understand what are the most important features in our models. Any questions before I keep going? Okay, lots more good stuff here. Okay, so far what I talked about was what are the most important features. The next question might be, what is their directionality? And this is where a tool called partial dependence comes into play. So what happens here is, and this is kind of a simple example I like to use. So consider the effect of age here. Down here we have our little baby dragons, and we can see how the model does on, for example, the dragons that are really young. We can look at their performance of we can take a look at the blue is the predicted performance of the model. If we want to understand maybe how the older dragons do, we can look on the far right side. You can see the older dragons have a little bit higher prediction because they get a little crankier, right? A little bit meaner, want to stay away from that. But the problem here is this tells us the effect of age in our model, but if you think about it, what's the weight of the models? If we had to compare the two categories, which category would have much lower weight dragons than the other? Right? These are the babies over here. They're going to be really low weight, while the older ones are going to probably have a much higher weight. So when we're looking at this, there's something else that's kind of correlated in there that's also another factor. We're really not just isolating for age by itself. There's other factors that come into play. Does that make sense? Okay. So that's where a technique like partial dependence comes into play, because it enables us to isolate what's just the effect of this one feature. So we only have an hour, so I'm not going to be able to go into, I'm not going to spend the time going through the partial dependence calculation. It's very simple, but it's 5 minutes I don't want to take. But I want to still illustrate the concept of it. And so I'm going to do it with a little bit different example here. This is a classic data set on the price of orange juice. Okay, it comes from Dominic's Supermarket, kind of a chain that used to be in Chicago. But let's step back and think about this. So what we want to do is look at the relationship between the price of orange juice and how much we sell. Okay. Right? We all took Economics 101. What's the general relationship? as I increase the price of orange juice, what's going to happen? It's going to sell less, right? A room full of people who've never actually sold anything, right? Because right, the reality is it's not nearly like that, because what happens is, yes, you can change the price of orange juice, but there's so many other factors that are coming into play, right? There's, for example, is there coupons, is there advertising? But the biggest one is, as you change the price of your orange juice, your competitors are all in the same thing, working and doing and changing their prices as well. So it gets to be a very complicated environment to understand what are the effects of just what you're doing. So if we look at this data set, and this is for one brand of orange juice, so it's like the Tropicana 128-ounce orange juice. And this is what it looks like when we just plot out the price versus the quantity sold. So there's a lot going on in the graph, so let me just walk through it. The blue bars in the background is just a histogram of the prices. So you can see, for example, there's 2 peak pricing periods that we sold at. The price here is per fluid ounce. You'd multiply it times 128 or whatever to get to the actual price of the product. But you can see, right, that for some reason, a lot of it was sold around 0.039 ounces, and then there's another peak over there. The orange line is how much we actually sold of the orange juice at the time. So here we can see, for example, when the price was 0.036, we did not sell very much orange juice, but right, when we increased the price, we sold a ton more there. Now, it's pretty easy to see that relationship between price and how much we sell here, right? Not at all. All right? It's not easy, obvious at all what that relationship is between price. And it's because there's a lot of stuff going on. Right? It's just not a simple kind of, you're not just looking at 2 things at once. So this is where a technique like partial dependence comes into play, because it allows us to hold everything else constant and just focus on what is the effect of just this one price. So this is what the partial dependence curve looks like. And here what we're looking at, we're just looking and trying to get the marginal effect of this feature. And when I do this, we get a nice little story. Now we can see, as we increase in price, right, generally sales go down. Kind of matches up with what, right, our intuition would be. But a couple of other things, right? You can see right around at that point where orange juice is $3.46, as soon as we increase the price, the sales drop. Why do they drop? Yeah, I think it's a human psychological thing, like that $3.50 mark. At that point, people are just like, maybe I'll get another product. Maybe I'll just get a smaller size. I don't want to pay $3.50 for my jug of orange juice. Right? You see something else happening at $4.23. Now, I'm not an expert in any of this stuff, but the idea here is to use these tools to explain what's going on in the model, and then sit with your experts, and you can tell the story of what the model is doing, and you can match it up with kind of what they're saying. But the idea is we just want to kind of take apart our model and understand what's going on inside it. Okay. Are people with me so far on this? Okay. All right. Okay. So, partial dependence. So Friedman, 2001, has the classic paper on partial dependence in one of the gradient boosted algorithms papers. One of the improvements that have been made along the way is by Goldstein, which uses something called ice plots, where the idea is that partial dependence plot I showed you is the average. Well, the average often conceals different types of behavior. Ice plots kind of blow that out, so you're not just looking at the average, but you're looking at that entire distribution. Sometimes that helps. It makes cool-looking plots. But that's another thing to kind of play around and check out with. There's implementations in R and Python for both partial dependence. It's a very widely used tool. Okay. All right. So please ask questions as we go through this. I have no sense of whether I should leave 10 minutes at the end or something for questions, or whether to just kind of keep it going like this. Okay, yes?
So I'll admit I haven't studied partial dependence, so how is it different than just running like a one feature simple model? I know you didn't want to go with the math, but I'm curious
So what we want to do with partial dependence is remember our model overall has lots of different variables or features, and we need to isolate the effect of just one of those. So remember, and what we're doing is trying to understand what's going on in our particular model. So once you have a model that has 10 features, there's no way to really just run it for one variable. Does that make sense? Right? Yeah. It's not that complicated to do it. It's just, yeah, I have limited time and I want to show you other cool stuff. Okay. Oh, one more question in the back. This one? Yeah, so in this one, I'm only showing the partial dependence curve. I'm not showing the predicted and actuals. Okay? Yep. Good question, right? So I've kind of been talking about this kind of, like in this one is just looking at one feature. When we have multiple features, we need to figure out which ones are most important. So the permutation tool will let us know and be able to rank the features to see which ones are more important than others. The other thing is when you look at the partial dependence, you'll see that as the feature changes, in this case price, it's affecting the likelihood, or in this case, it's affecting how much sales we have, so you can see what kind of swing it's doing from one end to another end. So these are ways to kind of assess how influential a feature is in a model.
Yeah, but I'm saying like once you have that, how do you know if it's statistically significant?
So the question is once we know that, how do we know it's statistically significant? And we can go statistically significant can open a whole box of worms here, because there's a group of people, statisticians, that care about that. There's a group of people, machine learning people, that don't care about that. So I'm going to take that hot little item and just put that aside. There are ways you can do bootstrapping and be able to get those kind of confidence intervals around those features, but you don't need to. You can still build models and understand them without that. But it's easy. You can do that if you want to. Okay, good questions. I like this. Okay, let's go. Let's talk about predictions. Right? At the end of the day, the value from our model comes from getting predictions out of it. So in this case, for example, right, the nice little blue dragon over here, we get a lower score because not going to likely to eat us, while the red one up there, right, really scary, stay away from it. Okay, and this is usually, right, the end point. We build a model, we get predictions out of it. Now, one of the things that's nice and you can do, and you should all expect this, is we can also get explanations. So what an explanation is we're going to build that model with, say, 10 or 20 different features, but we want to know what features are most useful for this particular prediction. So for this particular dragon, an explanation would say that based on this dragon, the number of past kills was the most important, followed by the color, followed by the gender. And the idea here is it gives us a little bit more context around this prediction. So let me explain this to you with one more example. So this is one of my buddies. He used to work in a hospital, and one of the things is this was for a readmission type model, but he would use these explanations all the time. And so the idea here is, this is a hospital, and we have probabilities of readmissions. Readmissions in hospitals is a big deal, right? When a hospital patches you up, they want you to go and not come back, right? They've properly done their job if you don't show up the next day with sickness. So part of their ethos is they want to make sure you're not going to come back, but there's also a whole set of regulations too that they get fined big time if people come back the next day. So this readmission problem is a very real problem for hospitals. So it's quite easy to build that model, get that probability. But what he also did was added explanations. So we could look at a particular person and understand exactly, well, what are the factors, right? Because they had 50 or 100 variables that go in the model. What are the variables that were most important to this person, for this person, that affects that readmission score? And when he first did this, he had a lot of pushbacks from the nurses. One of the things he quickly realized along the way is, you can see there, in this case, he has a kind of a readmission probability of 6. Learned that you don't want to give numbers. Nurses and doctors don't like numbers like that. It's just a lot easier to do green, yellow, red. He got rid of the numbers, right? There's a lot of this kind of stuff that, as data scientists, we're used to numbers, but he didn't. But they quickly, at first, were resistant to this idea of explanations, but they quickly came around to it and kind of thought of Data Robot or the explanations as kind of the buddy that gave them the reasons. And when you're having people, end users, that want some context, they want to understand those predictions, having these explanations is invaluable to getting buy-in for your particular model, okay? Because every situation I've always had is, as soon as that first prediction comes out of that model, people are going to go, why? What is it about this? Why is this person getting this prediction? Okay, are people with me on this so far? Okay. All right. Now, one of the most popular methods out there is something called LIME, Local Interpretable Model Agnostic Explanations. So I started digging into LIME a couple years ago, just before I joined Data Robot, and then Data Robot has its own explanation methodology, and so I found some issues with LIME, but I kind of had to sit on my hands because I was busy doing Data Robot stuff. But it killed me that all the stuff that you're going to find out that I'm going to show you here, I've known about for at least like a year and a half, just kind of sat on my hands with this. And then finally now, I think recently, people are kind of aware of some of the limitations of LIME. So let me start with our simple dragon here. So this is our red dragon. We run it through the model. We get a prediction, right? 9.1, nice scary dragon. But then I run it through the model, and I get an explanation. I have my friend in San Francisco, data scientist. She builds the same model on the same data, same seed, all that stuff. She gets a slightly different explanation. Is that okay? Can we just average out the explanations? It's all good, right? No? You guys uncomfortable with two explanations for the exact same point of data? Yeah, I mean, I think most people are. But one of the things that can happen when you use LIME is and this is just run on, in this case, this is the Boston data set, so this is just one of the examples in the LIME tutorial. You can run it, and literally, you can see there, I have the code. You can run it twice in a row and get, for the same data point, 2 different sets of explanations. Yeah, this is a little unnerving to most people, right? Because, I want to know what the most important thing is. I don't want it to change. It's hard enough to get people to buy into my model. Now these explanations are constantly changing. You're making my life really hard. So that's kind of a deal breaker too. I'll give you another one. So we have 2 dragons, and I picked 2 dragons that are at distinct ends of our distribution of dragons, right? A really scary, mean dragon, a really safe dragon, right? And we have, let's say, 10 or 15 features in our model. I run the model through. I get my predictions. But when I run the explanations, I get the same explanations for both dragons. Is that a big deal? Why?
Because they don't differentiate. Say that they're saying.
Yeah, but
Your explanation does not explain important factors.
yeah. I mean, this isn't really explaining this particular dragon, right? We're not really tying into the dragons. These might be the most important features overall in the model, but if I show 2 different examples, they got to be a little bit different, right? Why else do I have 20 features in my model if my model's not using them? So I think that intuition is right, but here's another one where, and you can just run this yourselves. If you go and run the LIME, and so this is on the adult data set. The idea is if you want to predict if somebody has higher than 50K income or less than 58K income. If you run it through, in the middle column here is the explanations. you'll see that every time I run it, I get the same factor as the most important explanation, which is capital gain. And in fact, if I take the 18,000 row test set and run it through, all the way through, I get capital gain all the time as the top feature out of that. Now, the reason it has it is because Lime makes some assumptions about the distribution of variables. So it assumes that all numerical variables have a continuous distribution. Well, I mean, if you work with real-world data sets, you have lots of zero-inflated variables, not continuous distributions, and so Lime kind of falls apart on this. In this case, in the capital gain is a very zero-inflated feature in the adult data set because if you think about it, most of it, or in this data set, most people don't pay capital gain, so it's zero for most people, but few people do. But yeah, so it kind of loses it here. Yep, question in the back? Great question. Does your explanations differ if you have different models? Absolutely. So what we're talking about here is we have one model, we've decided on the final model, now we're just explaining some rows in the data. A different model would look at the data differently, and you would expect maybe similar, maybe a little bit different feature impact. Could be similar explanations, but might be different depending on it. This is also why we use things like ensembles and blenders to combine models often to take advantage of the differences between different models. So the question is how would you use this for judging the robustness of another model? So there's a couple of things. A lot of times, right, the ways we judge the robustness of models is the overall performance. We have lots of other metrics for looking at that. Where I use this in terms of robustness is I will sit down with my subject matter expert and I will identify, in this case, maybe, let's grab 10 or 15 patients. Let's run them through the explanations. Let's see, do the explanations line up with how they would think about it, right? If my subject matter expert says, yes, that's how I would think about it, these are the same factors, that gives me a lot more confidence in understanding that underlying model. But this isn't a great technique for really comparing two different models as such. There's other tools for that. Okay. All right, more questions?
So what's the verdict on Lime?
Well, let's see, do I go there? So yeah, we have other and better techniques now to use. A couple of other things to consider that Lime does, and this is when we get to other explanation techniques as well, is there's a lot of talk out there where we build our models, and whether or not to use a surrogate model, a secondary model to explain our model. And this is another issue where Lime has, is because Lime assumes we have a nice, slow, rolling gradient of models, but the reality is if your XGBoost is full of all these discontinuities, right, harsh drop-offs, partitions, and so it becomes very hard if you're using a second model to explain it, to be able to explain and talk about kind of all those discontinuities. So that's one of the questions, issues you have is that. The other problem that Lime has is lots of hyperparameters. So this is another problem, right? If your explanation methodology has tons of tuning parameters that you have to deal with, then the question always becomes, well, how do I tune it, right? So with Lime has a notion of neighborhood, right? And right, a neighborhood is very different if you're in downtown Nashville than if you're 20 miles outside of Nashville, right? I mean, the concept of neighborhood has a great deal of variation. Same kind of things in your data set. So this is where it can get a little tricky figuring this out. And I think at this point, like people like Molnar have kind of made enough points to kind of point out some of the issues with the Lime methodology as well. So the other piece I like to make is that we like explanation methods that are model agnostic because we know there's lots of different model agnostic techniques that are out there. We also want techniques that are fast. Some of the explainers that are out there are very slow. So Lime takes about half a second to do an explanation, which if you're a student and you're running a project, that's fine. But if you've got 10 million records for a marketing campaign to run, half a second, I mean, that's adding up to a lot of time. Okay. So where do we go from here? So don't use Lime. There's much better kind of ways to go. There's a number of new techniques really led by the use of Shapley values, and we'll see how much time we have if I can dig into those a little bit. But the use of the Shap package and the concept of Shapley values has really changed, and that's the preference instead of Lime. There's other approaches, Live and Breakdown by BSIC as well, that use the same notion of kind of Shapley values in terms of using for explainers. The other thing I wanted to point out is how we set up our explanations, how we show our explanations can affect fairness. That's the paper by Dodge as well. All right. I've gone through a bunch of stuff. I want to make sure kind of at a high level we understand. Right? We have tools for figuring out what features are most important in a model. We can rank those. We can understand how that particular feature is affecting it, isolate just the one feature, understand that directionality. And then the last thing we can do is we can explain examples. So whether rows in the data set, whether people, dragons, we can help give some context for each prediction. So there's lots of technologies, standard off-the-shelf open source technologies for doing all of these. This is, I think, really kind of table stakes and should be expected of any model that either your data scientists are building or data scientists are bringing you. Okay. So I can show more cool stuff, but I want to make sure I answer kind of questions before I keep going. Make you guys sit there forever. Yes?
Can you explain the methodology?
I can. I have it in my skip slides, but for you, we can go back and go through it. It's good. All right. Okay. So here's the way partial dependence works, is what we want to do is we're going to take one dragon, we're going to take our red dragon, and what we want to do is we start with that red dragon, we take all the values of the red dragon, pass them through our model, get a prediction. So we know, for example, if that dragon is 15 years old, what the prediction is going to be. Then we're going to vary the age of this dragon. We're going to say if I have the same dragon and it's 5 years old, what's the prediction? If I have it at 50 years old. And we're going to just plot that out, starting with one dragon. Does that make sense? Are everybody with me so far on that? Okay. So we start with one dragon. Then what I want to do is get another dragon. And I'm going to do the same thing. And in this case, this dragon has different characteristics, so the points are a little bit different for the predictions. And I'm going to plot that out. But I'm not going to stop there. I'm going to go get more dragons and plot those out. Once I do that, this is that notion of ice curves that I told you, being able to see all those different lines. It shows you the ice curves. But then what we do to get partial dependence is we take all those different lines and we bring them together and get the average. And so that's how we can figure out what is the effect of age holding everything else constant in our models. Does that make sense? Yep.
Do those lines ever have any kind of skewness that would make averaging them make sense?
So the question is do those lines ever have any skewness to them that maybe doesn't make sense averaging them? That's exactly, typically in most cases that I've seen, it's fine to average them, they aren't. But there are times when you have, for example, interactions where it makes sense to look at those ice curves because you can see that taking the average is losing some information. So yes, you can use tools like ice curves to kind of, if you want to probe in further for that. So yeah. Mm-hmm. Okay. More questions? Okay. I'll leave you with the one. So I kind of teased you with the Shapley values. Let me explain to you kind of what Shapley values are and kind of why they're kind of taking over explanations. And Shapley values, I'm not doing the build outs, but you'll get the words. It's okay. So Shapley Values comes from cooperative game theory. The idea is, and the example I like to use is, I have a teenager, he's 17 now, driver's license, wintertime, I live in central Illinois, we get snow, he gets the car stuck. So then we got to go out and push it. So it's usually me, him, we grab one of the other teenagers, and we got to go out there and rock the car out of the ice and snow, right? And whenever I'm kind of there pushing on it, I want to get this done. I want to get the car out and go home. I'm kind of putting my back into it, really pushing hard. But I look over at the other teenagers. I just really think they're just like, touching. I don't really think they're really pushing it. I think they're just kind of like, hey, let's just watch dad sweat kind of thing. What Shapley Values does is it wants to figure out what the contribution is for each of the people pushing the car. So how much is it me that's pushing the car out? How much is it kind of teenager 1? How much is it teenager 2? Can we apportion that out? And that's the concept of Shapley Values that's being used. And so what happens is we want to be able to calculate and understand the effect of each one. Now to do this, if you really want the real Shapley Values, you have to calculate it for every possible combination. If it's just me there, if it's just my son there, if it's both of us, if it's all three, all those different combinations, then you can figure out what is the contribution of each. But the problem is this is the tricky part, is it doesn't scale, right? Because the problem is as I get to 50 kids pushing a bus, figuring out the contribution of each of those gets very complicated. And so this is where much of the literature around Shapley Values, it's really good, but we're back at another thing, just like permutation, where we have to do approximations. There's a number of different packages. IML does a strum ball approximation. In the SHAP package, they use, for example, a SHAP kernel, which creates that surrogate model, which I'm not too keen on. There's the tree SHAP, which is really good, really awesome, only works for tree-based models. So that leaves out lots of worlds. But those are some of the kind of the more of the cutting edge ways of how people are actually kind of doing explanations nowadays. All right, I think I have to let you guys go. I'd keep talking for another half hour. Any last questions here? Okay. Feel free to contact me, hit me up, LinkedIn, Twitter, whatever. Always happy to kind of talk about this stuff as well. So, all right, thanks.